Hi, welcome to a video where we are gonna practice solving some exact differential equation, finding potential functions from these exact differential equations. And the last video what we covered was what they were, why they are the way they are, where they come from, and how to solve them. Right now we're just going to practice, and like always, I'm going to give you lots of examples because I want you to try them on your own. I'm going to give you some that I think are a little more difficult towards the end. That way we can see how to work with initial values. So that's our last problem. I'll show you where that is. If you want to skip there and just see that one, that's fine. I will also show you that whether you integrate m with respect to x or n with respect to y first, it doesn't matter. So I'm going to show you that on the last example as well. So let's get right to it. I'm going to discuss with you and kind of review what an exact differential equation is as we go through this. But mostly this video is about the technique of solving them. So we're just going to get some examples under our belt. That way you feel very confident going forward. The worst thing we can have is for you to go forward and not feel like you know what you're doing. That's an awful feeling. So I'm going to make sure that you do feel good about your understanding of this stuff because you really can get it. So let's take a look at this. And the first question that you're going to be asked is that an exact differential equation? And you're going to look at it and probably you're going to go, yeah. And that's wrong. That's a mistake. And the mistake is that's not an exact differential equation of some potential function unless it satisfies a very specific quality in that the mixed partials would be equal. Why is that? Because in order for a potential function f of x, y equals c to have this sort of a form of a total differential or an exact differential, the mixed partials would have to be equal. Saying it came from some function where it was continuous and differentiable on some region. And so what we're doing is going backwards from that. We're saying this is only an exact differential equation of some potential function if the mixed partials are equal. Because if that's the case, then it is coming from some function that was continuous and differentiable on some sort of region and would have given us this differential. I hope you understand the very specific nuance there. It's really important. You're just looking and go, yeah. Because if the mixed partials aren't equal, then no, that is not an exact differential equation of some sort of potential function. So we're going to check that first. That's a first step. Last video I gave you some nice steps on how you go through, and we're going to explore those. So step number one, we're going to typically call this m and this n. M is the piece, this partial derivative of f with respect to x that's joined to the dx, and the n is this piece, this partial derivative of f with respect to y that's joined to the dy. And we're going to say, all right, well, if m is the partial derivative of f with respect to x, so this is m. And if n is the partial derivative of f with respect to y, this is that. So that's all well and good. How do I do my test? Guys, if m is already the partial derivative of f with respect to x, then the mixed partial would take this and just do the partial derivative of m with respect to y. Or in this case, if you don't remember partial derivatives, you really need to go back and check that out. But in this case, we say, well, that'd be like an x, sorry. That would be 0. This would be 1 over x. Because those x's would be held to be constants. Now, they don't go to 0 when you take a derivative of something like this. They're treated like constant coefficients. So you'd get 1 over that constant. So like derivative of y over 2 would have given you 1 over 2, 1 half y. So it would give you 1 half. Here we're just going to get 1 over x. I hope that makes sense to you. So one more time, I'm not going to go through this an awful lot, like really slowly, because that was the last video. We say, all right, hey, this piece, that is m. That's what we called m. So if I want to find a mixed partial, I just take the derivative of m with respect to y, and that would give me x, then y. Likewise, the partial derivative of y with respect to x says, well, this is already the partial with respect to y already. So if I want to find the partial with respect to x after that, a mixed partial, I would take the derivative of n with respect to y. Well, I said that wrong. the partial derivative of n with respect to x. This is already a partial with respect to y, so I'm just going to go, I want the partial with respect to x, a mixed partial, and that's fine. Just look at n, take it with respect to x. So all the y terms, that's a constant, that's gone. But the derivative of ln x with respect to x would give you 1 over x. Oh, that's nice. That right there, when that happens, what that's telling you is that, yes, now you can make the determination that this is an exact differential equation. For some potential function, f of xy equals a constant. Now we can say that. Now we can say, because these mixed partials are equal, they're representing a function, look at that, a function that is continuous and differentiable on some sort of a region whose differential form or total differential would have been this, exactly this. Now we can say it's worth our time to go backwards. Because this is true, we can now find that potential function. How you do it. And I do this every time. I always write my mixed partials here. I always do my structure here, partial derivative of f with respect to x and y, respectively. And then I look at, because I want to see it, I really want to look at it, and I ask the question, which one's easier? Is it easier to take an integral of this with respect to x or this with respect to y? Because the point is, if we have a derivative, how you undo derivatives, if we have a derivative of a function, how you undo derivatives is with an integral. We're about to take an integral, and you're going to have to choose either m, take the integral of m with respect to x to undo x, getting the function f, or n with respect to y, getting rid of the y, undoing that derivative and getting f by taking the integral with respect to y. Either one works, it doesn't matter. Sometimes they look about the same, so this would not be hard to take an integral with respect to x. That's not particularly hard to do an integral with respect to y. It really doesn't matter so much. I would say that one looks easier to me because we get this natural log, that's fine. Ln x, we already defined that x would have to be positive even to be up there, so we're not going to have any strange domain issues with that. So I'm going to do that. So if they look about the same most of the time, I would suggest to you, because most textbooks do this, to just pick the integral of m with respect to x, because we're more familiar with that. But if this is considerably easier to do with respect to y, that integral, then you do that one. And I think I showed that in the last example, last video, but I will show it again at the last example of this video. So let's do it. Again, the idea, the going through idea. Make sure it represents the exact differential of a potential function. Then we're going to undo this derivative with an integral. We're going to take the derivative again with respect to the opposite variable and set it equal to this thing. And we'll talk about that right now. So that's the exciting part. Here we go. So if we have this as the partial derivative of f with respect to x, then f itself would equal some integral of m with respect to x. Great, let's do that. It's not too bad. Then this would equal, let's see, x to the 4th over 4 plus y ln x. I don't need the absolute value because we already defined that x would have to be positive just by having this function. The domain is implied. So this would have easy integral. This one, hey, that's a constant. That's like 2, all right? So we would have 2 ln of x, but now the y is held constant when we're taking a derivative with respect to x. Now here's the issue. I spent a long time on this in the last video. Because this is coming from a partial derivative, because we're integrating this, if we wanted to get this back, every function that would have just y's in it would go to 0. For instance, if I took this and I took a derivative with respect to x, it would have to equal m, and let's see what that would do. The derivative of this with respect to x is x cubed. The derivative of this with respect to x is y over x. The derivative of this, everything would be in terms of y, is 0 with respect to x. That's why instead of just like a plus c, you've got a function of y's. Because under partial derivatives with respect to x, all of them would disappear. We have to represent that. It's incredibly important for you to have that. Don't put a plus c here. Put a function of y because this is coming from a partial derivative. with respect to x. All the y's would have canceled. So if you're not okay with this right now, you need to go through, just listen to where this is coming from one more time, and then we're going to move on right now. So we know that's a partial of f with respect to x. We undo it with an integral. We say because it came from a partial, all the y's, had we taken that derivative, would have gone to 0. So we're representing that with a function of y that we don't know. Now here's the magic, the cool part. This is your function f of xy. This is it. It just has a piece that's going to be all y's that we don't know. Now, we do know something about a piece of that differential that's all y's. We know n. We know n is the partial derivative of f. This is f with respect to y. So wait a minute. If this is the function of f, just a little piece I don't know, and this is the function of f under a derivative with respect to y, let's take a derivative of this piece with respect to y. That would be 0. It's a derivative of some x's with respect to y. That's 0. This would be just ln x. This would be the derivative of the function with respect to y. So we've said, okay, man, this is the function. Just integrate m with respect to x. This is the function. It just has some y's I don't know. This has some y's I do know. Let's take a derivative of this with respect to y. Oh, yeah, that's pretty easy. But wait a minute. Isn't this itself the derivative of f with respect to y? Yeah, and they have to be equal. This is what's going to let you solve for that missing function, or actually the derivative of the missing function of y's that you don't know. So take the derivative with respect to y from what you found upon integrating. Really quickly, I'd say integrate x derivative y. Integrate y derivative x. And then you set them equal to the opposite thing. So you take your m, integrate, set equal, take a derivative, set equal to n. If you integrate n, take a derivative, set equal to m. So here we say this derivative of f with respect to y that we got from here, these are the same exact thing. You have to set them equal. So this is going to equal n. I mentioned also in the last video that a lot of things are going to cancel out. And yes, you should end with something that just has y's in it. All of your x things, all of your x terms, they need to go away. Because when we take our integral here, we say, man, how do you undo derivatives? We just do an integral. So if we integrate both sides, we're going to get that g of y is 1/3 y cubed. We also talked about how the plus c is not really relevant. I'll talk about why that is in just a moment. But we integrated m with respect to x. We take a derivative with respect to y, and now we set it equal to what it has to be equal to. And we solve for it. We solve for the derivative of the function we didn't know. We integrate it. It gives us the missing piece. So now right back up here, man, I wasn't lying. That is your function of f. But now we've actually managed to figure, oh, that's so cool. We managed to figure out the missing piece here. So we know that the function of f with respect to x and y is, it is this, and this, and this. It just took us some time to find. It took us the realization that taking a derivative with respect to y is going to set it equal to n. Solving for the derivative of that lets us do a very basic integral to find that missing piece. And because the potential functions are always level curves, they're always two variables set equal to some constant, we're going to show that that equals c. So the final answer here, the potential function that would give us that exact differential form, is this. I mentioned to you a minute ago why we don't need a c. If we had a plus c, that would be right here as a constant. I would just have to subtract that to the other side, and it would still be an arbitrary constant. So it really doesn't matter to include. And most people don't show a plus c here. If you did, you would just subtract it over and you'd get a different arbitrary constant, which doesn't really make a difference. I hope that that makes sense. I hope that my explanation to you kind of reinforced the process of finding these potential functions from exact differential equations, and really importantly, that you can't just look at it without doing that mixed partial and say that's an exact differential equation. The exactness of it, the exact differential equation part of it, comes from testing the mixed partials and then saying, okay, now it is, I can guarantee, an exact differential equation from some potential function, and we go through and solve it that way. So the next one I'm going to go quite a bit quicker. I think I re-explained the entire last lesson right here, which is good. You should see it again. But really it's check your mixed, take either m or n, integrate with respect to the variable you have a derivative of, then take a derivative of the different variable, set it equal to the opposite thing. And that should make sense when we get the hang of it. So I'm going to go through one more here. I'll give you about 3 more, and we'll have some great practice under our belt. All right, so let's do it. The first thing we want to check is some mixed partials. Let's see if this is actually an exact differential equation. So we're going to call the part that's next to the dxm and the part that's next to the dy n. So we know based on the form of our differential here, that if this is an exact differential equation or exact differential form of some sort of potential function, then this right here is our m, and that's the partial of f with respect to x. So I always write that down. And this would represent the partial of f with respect to y, if this is going to be an exact differential equation. We call this m, and this n. Now let's find our mixed partials. Because m represents the partial derivative of f with respect to x, we just have to take that piece with respect to y. So here we'd say, let's see, with respect to y, that would be 0. This would be, I'm looking at factors in my head for you, I'll show it to you. This would be derivative of the first times the second plus the first times the derivative of the second. Now let's see, derivative here would be, we have y, we have e to the xy, but by the chain rule we get an x. So that's e to the xy plus y e to the xy x. Remember that this derivative with respect to y would go to 0, but this is a product rule. So derivative of the first is y, leave the second, plus the first, that's our y. Derivative of the second is e to the xy times chain rule. Chain rule says derivative of xy gives you x, because that would be held like a constant there. Oh man, okay. Or the derivative of f with respect to y, then x is a mixed partial. So now x, this would go to 0. And then this with respect to x would give you derivative of the first is 1, that's e to the xy, plus leave the first, that's x. Derivative of the second, well, that's e to the xy. But the derivative of this would be, again, a chain rule. And you say the derivative of xy with respect to x now, x would be the variable, y would be held constant, and those are exactly the same thing. It might take you some work to go through those if you get a product rule, but this is exactly the same as that due to the commutativity of multiplication. What that says is that, hey, that is now called an exact differential equation of some potential function. Let's find it. Now we're going to look back here and say which one would be easier for us to find an integral. Would it be easier to find the integral of m with respect to x or n with respect to y? I would say that one with respect to x. So let's do that. Does it really matter? It doesn't really matter. Sometimes it matters a lot because one's way easier, but it doesn't really matter. You're going to get the same answer. So let's do this. Let's say that, hey, the partial of f with respect to x, this is where we're starting. That's m. That's 1 plus y e to the xy. Okay, so if that's the derivative of f with respect to x, as far as the partial derivative is concerned, then if we integrate it with respect to x, it should give us our function back. Mostly. The only thing it won't do, well, it won't give us any sort of terms that just had y's in them. We call that a function of y. Those would have all gone to 0. So we're going to say that, yes, this function is going to be the integral of m with respect to x, let's see how we do this. We take, that would be held like a number like 2, so it would be a y. Exponential would be, give us that back. But man, if you did a u sub, you did that u sub there, you'd get du equals, with respect to x, y dx. What's really happened is you have an integral of 1 dx plus an integral of y e to the xy dx. This is going to give you obviously an x. But in this case, when you do your u sub and you say, hey, du is y dx, it replaces this whole piece. You call it u du. And then we'd say x plus e to the u, but u is xy. So we're going to get this x plus e to the xy. It's good to see those integration techniques from time to time. Any way you go, you're going to do the same thing. I'm going to erase this, but just a u sub here. Okay, so what have we done now? We have it wrong, first off. We have it wrong. The reason why we have it wrong is because every time you do an integral, you should get a constant. Or you should get something that would be held constant considering where it came from. Because this is a partial with respect to x, any function of y would have been held as a constant. It would have gone to 0. And so we're going to say any terms that just had y in them would have gone to 0 here. So we've picked m, we integrated x, and we have a missing function of y. Now we're going to take a derivative with respect to y. So we picked the derivative of m and integrated. We're going to take a derivative of y. And that's not hard to do. This is 0. This is going to be x e to the xy by that chain rule, and a derivative of the missing function of y. And that has to be equal to m. So again, it's going to start, I'm going to say it a lot here. Integrate m derivative equal to n, or integrate n derivative equal to m. And so here we did integrate m derivative has to be equal to n. And that's why I write it down, so it's nice to see. We just took a partial derivative with respect to y. It must be equal to this thing. If you are not canceling out your terms that have x here, you're doing something wrong. This missing function can only be in terms of y. And so this stuff, a lot of it's going to cancel. We're just going to get 2y. Man, that's kind of nice, because we know how to undo derivatives. Since this is the derivative of g with respect to y, we know that we can integrate both sides and say this is just going to be whatever the integral of 2y dy is, or y squared. So that missing piece is just y squared. Since we got our function right here, and we just didn't know that piece, this is the only reason why we did all this stuff. We did this another partial derivative to set it equal so we can solve for that piece. And now let's put it back. So f of xy, it's this stuff, it's the x. It's e to the xy, and it's the function g, which we just solved for as y squared. It's nice. And we know that that's going to equal a constant coming from the level curves. That's our potential function that we just found. So we're going to write it that way. One more thing, if you're able to solve for y here, a lot of times that happens. So if you're able to solve it for y, and that's fine also. We can't in this case, it's implicitly defined. But you could do that. Also, if you had an initial value, that's where we plug it in. We'd say like, hey, y of 0 is 1. We'd plug in 0 for x. We'd plug in 1 for y. Let us solve for that arbitrary constant into a particular solution. So I hope that's making sense. We've got a few more to do here. I'll be back in just a second. Let's get started on a couple more. If you can, I would pause this, at least try to do this much of it, get it set up properly on both of these examples, because we're going to go through them fairly quickly. We've kind of got through the time of explanation, like the full explanations, and now it should start really making sense in your head. Now's our time for practice. And in a class, and you are my students right now, I would have you do it just on your own. I'd be walking around and seeing how you're doing. I can't do that, but I would really like you to walk through that. So let's do this together now that you've hopefully paused the video and tried this on your own. the number one thing we need to get straight is the fact that this is not an exact differential equation until we satisfy that test. So let's call this m and n, and let's write down these things. So if m represents the partial derivative of f with respect to x, which this is the differential form, that's what that does, then m is this piece. And I'm always writing this down. It's really helpful for us, our brains, to see what's going on. Most of us are visual learners. And so by writing this down, you are cueing your brain, and you're seeing it, you're cueing your brain to see m is this thing. The partial derivative of f with respect to x is this thing. Likewise for n. What that means is you're less likely to integrate the right thing with respect to the wrong variable. Okay, so now that we have the partial of f with respect to x and partial of f with respect to y, we're going to find our mixed partials. We're going to see if this is an exact differential equation. So we're going to find the partial of m with respect to y. That's 0. That's 1 over 1 plus y squared. And I always set it up like this. Okay, now the partial derivative of n with respect to x. This is 1. This is a held constant. So we get 1 over 1 plus y squared. That right there is what you're looking for. Actually, maybe you're not. Maybe you're like, I want to be different, though I don't have to do any more work. If they're different, it's harder, because we're going to find an integrating factor in the next video that's going to let us do stuff like that, but it's much more work. And so you kind of want that to happen so you don't have to deal with an integrating factor to change this into an exact differential form. So that right there says that's an exact differential. Let's keep on going. Pick one of these that looks easier to integrate. Either this with respect to x, I'm doing the partial, or this with respect to y, I'm doing the partial. This with respect to x looks much easier to me than integrating this with respect to y. So I'm going to pick this one. I'm going to integrate this. So because the partial of f with respect to x is x plus tan inverse y, then the function of f itself would be the integral of that. So we're going to integrate x plus tan inverse y with respect to x. And that's not that hard. What we do need to understand is that we are integrating, we're not taking derivatives here. So yeah, you're going to get this x squared over 2, that's not a problem. But this doesn't go to 0. That's held as a constant, so that's like 2, which means you would get 2x, or x times tan inverse y. But you're also going to get a constant. Only that constant would be everything that would just have y's, because it's coming from a partial derivative with respect to x. So we're going to say g of y. We use g as a function for y's and h for the function of x mostly. Okay, hey, this is the function. You know what? We have all the x terms that we need. This is it. This is going to be in our final answer. What we don't know is, are there any terms that would just have y's? If there are, then taking a partial derivative of f with respect to y, 0, this is just x times 1 over, let's see, 1 over y squared plus 1. So this is a multiplication. That would be held at a constant like 2. You would get 1 over 1 plus y squared. That's that tan inverse y plus g prime of y. If there are any functions, any terms that just have y's in them, taking a partial derivative will let us solve for those, because this right here has to be equal to n. This is n. We took a partial with respect to y. That is n. So let's set it equal. And you go, I thought you said all the x stuff is going to cancel, Leonard. And I go, it is. It just looks really funny. So what I actually told you was solve for this, and then all the x stuff is going to cancel. So if I subtract this, then the first derivative of g with respect to y is x plus y over 1 plus y squared minus this piece, x over 1 plus y squared. And I hope you're seeing it. That has a common denominator already. If I subtract, my x's are going to cancel. G prime of y is just y over 1 plus y squared. And there's only one more thing we have to do. We've got to integrate this to figure out the missing function of g. So we're going to integrate. Looks like we're going to have a u sub here. Integrate with respect to y. You only have y. Shoot, it said it was a function of y. Let's solve for y dy. Let's say this is 1 over u du over 2. And what that's going to give us is this ln, this 1/2 ln u. We're not going to do the absolute value. This can only be positive anyway. And we would get a plus c, but we determined that's really not necessary, because if we had a plus c, then right here, when we put that g of y, if we had a plus c, when we put that right back here, that plus c is going to get absorbed into another arbitrary constant anyway. So we're done. We found the function with the missing function of y. Took a derivative, found the derivative of g with respect to y, with y. We solved for the function itself, and now we're ready to put it back. So the function is, we have an x squared over 2, no problem. We've got this x tan inverse y. That stuff is going to stay. That's fine. We want that. The missing function of y was all we really wanted. So if you have x's when you're done, you've probably done something wrong. And we would say that right there is going to be equal to c. And so if you would have had this plus c right here, it would have been just absorbed anyway. I'm going to leave it right there, but I hope that I'm making sense to you. I hope that when you're walking through this on your own, you're able to follow the logic down. Right now, it should start being internalized for you, saying, yeah, I understand that if I'm going to integrate m with respect to x, then I'm going to have a missing function of y. And if I integrate n with respect to y, I'm going to have a missing function of x. I hope you understand that taking the partial derivative of the variable that's opposite of what you just integrated with respect to is how you solve for that missing piece. So take an integral of m, you're going to take a partial of y instead of equal to n. Take an integral of n, take a partial with respect to x instead of equal to m. It's just the opposite. Let's try, wow, that one looks nasty. Let's try this one. Where do we start? We start by thinking, if this is an exact differential equation, then that would have to be the partial of f with respect to x. That whole gorgeous piece would have to be the partial of f with respect to y. And man, we're going to write that down. We're going to say that m is this, n is all of this, and now we're going to do our test. We're going to find our mixed partials. So we're going to take the partial derivative of m with respect to y and n with respect to x. We're going to see what we have. So m with respect to y, man. Well, that part's pretty easy. This part, remember that this would be 2x y to the negative 1. So I'm showing this. You should show this. The derivative would be, let's see, negative 2x to the x y to the negative 2. So negative 2x over y squared. That one's not bad. With respect to y, that would be negative 6y over x to the 4th. All right, next one. Man, with respect to, good thing that's with respect to x, because that's going to go to 0. I like that. But with respect to x, so this is let's see, 2y x to the negative 3. Bring down the negative 3, that's negative 6. X to the negative 4. So we have a negative 6. We'd still have a y. We'd have over x to the 4th. Now this next one, with respect, remember this is with respect to x, so we'd have 2x over y squared. This would be with respect to x, so 1 over just a function of y would go to 0. Oh, great. Hey, they're the same. Look at that, they're out of order, but that doesn't matter. Right now what we've proved is that that's an exact differential equation for some potential function. Let's find it. Now, which one is easier to integrate? Either this with respect to y, that's math, I don't want to do that, or this with respect to x. Neither of them look good, but this one looks a lot better. Do you see the point? I would not want to integrate this with respect to y. It looks really junky. Don't do that. Do the easier one. Now, I've given you like, what, 4 in a row now, where this is the easier or it doesn't matter. So the next one, I'm going to give you, this would be easier to integrate with respect to y. So we'll check that out in just a moment. So let's go for it. We know right now that the first, or the partial derivative of f with respect to x is this junk, this 2x over y minus 3y cubed over x to the 4th. Because that is the partial of f with respect to x, getting the function itself, that potential function itself, involves an integral of that m, and undoing the derivative with respect to the same variable. So undoing that with respect to x. Okay, well we can do that. That's not super hard. Just a partial derivative, for goodness sake. So x, let's see, 2x over y. If we integrate that with respect to x, y is held like a constant. So you could think about this like 2/3 x or something. Let's see, we add 1 to the x exponent, so that would be 2, divided by the new exponent, that would be divided by 2. We're going to get x squared over y. Remember, with respect to x. With respect to x, this is treated as 3y squared x to the -4, where that's just like a number, like 5 or something. Let's add 1 to the exponent, that's -3. Divide by the new exponent, that's divided by -3. So this would be a 3y squared x to the -3 over -3. Those 3's are going to cancel. We're going to get x to the 3rd on the bottom, and our sign's going to change. But most importantly, where I see a lot of students just kind of make a mistake here, what they do is that they'll put a plus c, they'll forget it, and then they'll take a partial derivative, they'll set it equal, and everything will cancel. And they go, what have I done? Or nothing will cancel. And they go, what have I done wrong? I'm not solving for anything. We have to understand that there is a constant here, but it's any terms that would have been in y's only. Those would be held constant, so we need to have that. Now we say, if that's our function, we're missing a piece, let's take a derivative with respect to the variable that I didn't just integrate with respect to. So integrate x, take derivative y. This right here, remember that's a -1, so let's see, negative x squared over y squared. With respect to y here would give us a plus 2y over x cubed, and then we get this derivative of y. So let's see, we picked m, integrated x, derivative y is n. We set it equal. So this has to be equal to all this stuff. Hey, that's wonderful. Because if we add this to both sides, this is gone. Everything involving x would have to be gone here. If we subtract this from both sides, this is gone. And we get that the derivative of that function of y that we really want to know is 1 over y squared. Sorry, I said that wrong. 1 over the square root of y. So the function we're missing would be the integral of that. So the integral of y to the -1/2 dy. Oh, that's nice. That means the function we're missing is pretty basic. Let's see, we add 1, that'd be y to the 1/2 over 1/2. That's 2 square root y. Perfect. We just found the missing function. We just wrap this up. We say, hey, now that we found this, we know that the function I was looking for is this piece. And the missing piece that I found by taking a partial with respect to y and then integrating after setting that equal to n is just 2 square root y. That looks really good. That's about as far as we go. We can't solve for y. If we had an initial value, we plug it in right there to solve for that c. Man, am I getting through? Am I really making it sink in? We've done a lot of examples, taking a long time. I understand that, but it's useful because there's some. Well, I wouldn't say it's just incredibly hard to do. There's some nuance. There's some really fascinating things that have to be done just right in order for us to really follow them. And the better I can explain it, the more likely it is to stick with you. We have one more. What I'm going to do in the last example, I'm going to show you how we can pick this and integrate y, and then take a derivative with x and set that equal to m. So I'm going to do that one. We'll also talk about initial value. So hang on, I'll be right back. All right, we're on a roll, so to speak, so let's finish strong. We got something that looks really nasty. Don't worry, it's not that bad. It just looks really bad. This example is just one that I want to really reinforce that it doesn't matter what you pick. I've been talking a long time about that, and where initial values come into play, because I'd be remiss if I didn't put something in there for you as far as that one. So let's go through it. I'm not going to go super slow. Let's make sure that we're all just understanding where this is coming from. If you want to try on your own, that'd be, man, the best thing that could happen right now is if you do it on your own and get it right. If you don't, that's okay. You're still learning it, but try it. So is it an exact differential equation? Let's find out. Man, let's find out. Let's call this m and this n. And let's see what happens when we find our mixed partials. So if this right here is an exact differential equation, then this would be the partial of f with respect to x. And likewise, this would be the partial of f with respect to y. Now let's find our mixed partials. This means if this is already a partial with respect to x, take it again with respect to y, and that gives you this right here. Partial of n with respect to y would give you e to the x plus x e to the x. Looked bad, not bad. Or, since this is already the partial with respect to y, take it again with respect to x. Now that's 0, but that is a product rule. So you're going to have derivative of the first, that's 1, times the second, e to the x, plus the first, x, times the derivative of the second, e to the x. And that's exactly what we want. We want our mixed partials to be equal, saying this is coming from some potential function that's continuous and differentiable on some sort of a region. That's it. That's all it says. It says we can basically keep going. Now we look at m and n. Which is easier to integrate? This with respect to x. Really? You want to integrate that? I don't integrate that. That's horrible with respect to x. That's not super fun. I don't want to integrate this because this is a problem. Not a problem. This is a problem. This would make it really nasty. Now, could you do it? Yes. Do you have to? No, don't. Let's look at this. Take this and say, can I find the integral of this with respect to y? You go, but I don't have any y's. Exactly. That means that that's all like a constant. That means it's really easy to integrate. So let's take n. Let's say, hey, the partial derivative of f with respect to y is n, and it's really easy. It's x e to the x plus 2. We see, if that is the partial of f with respect to y, then the function itself can be found by undoing that derivative with integral with respect to y. So how do we do that? There are no y's. Yeah, no, they're all constants. So our function of f with respect to x and y would then be x e to the x times y plus 2 times y. You see it with 2 pretty easily, right? You say the derivative of 2y would give us 2, so the integral of 2 would give us 2y. Likewise here, x e to the x is constant when we are talking about y as our variable. The only issue here is that we have to understand this, that because this came from a partial derivative with respect to y, and we're integrating with respect to y, there is a function of x that would have gone to 0 when we took a partial derivative. Check it out. If I take a partial derivative of this with respect to y, this would give us that. This would give us this, and anything in only x's would go to 0. That's why this exists. to say, hey, there's some x's here that you probably don't know. Let's find them. How? We just integrated with respect to y. It gave us something that has x's we don't know. Because we integrated with respect to y, undoing the partial with respect to y, we haven't really considered the partial with respect to x yet. Let's do that. Let's find the partial with respect to the variable you didn't just integrate. So the partial of f with respect to x is, well, now we are going to have this, this product rule. So with respect to x, this is going to give us x plus e to the x. Did that wrong. It's going to give us e to the x plus x e to the x times y. That's a big deal. Because we have this product rule here as being multiplied by y, that y is a constant, right? So it would have to distribute across that product rule. I would encourage you to do it this way first and then distribute it, but there are a couple ways you can do it. So the main thing here is to recognize, yeah, that's a product rule. Derivative of the first, 1 times the second, plus the first times derivative of the second, but you are multiplying by y. Can you see how a lot of people would, if they forget those parentheses, are going to really mess us up? So be careful with that. The second thing that I want to do, I want to acknowledge that that's a y with respect to x, that goes away. This right here says, hey, you have this derivative of some function of x with respect to x. It's still going to be there if you have any terms involving x. And then we understand that that partial derivative of f with respect to x is what we called m. So it's got to be equal to m, this thing. You see it? Super nice. You go, well, if I distribute this, start subtracting stuff. Whole reason why I got into math, man, I just love crossing stuff out. Because you can make sound effects like Star Wars. When I was, it's probably horrible parenting, but I grew up in the Star Wars generation, and it's probably too much information for you guys anyway. But when I was 3 years old, my parents started letting me watch Star Wars. Bad decision. By the time I was 4, I'm not even joking you, I had memorized every line to the first Star Wars Episode 4. So dorky, but like as a 4-year-old, I just walk around. It doesn't matter. Anyway, I love crossing stuff out, and everything crosses out. Have you done something wrong? No, you haven't done anything wrong. All this means is that you have no function of x that's just x's. What do you do then? When you take an integral, it's just going to give you a constant. So if the first derivative of a function of x is giving you 0, then that function of x, that looks really awkward. Yeah, it really is awkward, but that means that all you had was at most a constant here. No x's. You'd have at most a constant. So, and let's call that c sub 1 because I want to really show you one last time where that comes from. So we had our function with the missing x. There actually aren't any missing x's. This is it. You could kind of confirm that by taking a partial with respect to x and getting this, partial with respect to y and getting exactly that, and you go, oh yeah, there really aren't any missing x's. But we go through the process, we confirm that right there has no x's. It would just be at most a constant. So let's write that. So our missing piece is a constant. Now, if we solve this for just our x's and y's, if we subtract that constant, do you see how a constant minus a constant is still a constant? I'd really encourage you to do that first before you start trying to solve for your initial value, otherwise it gets a little bit awkward. So now, now that we've solved for the potential function, now we get to use our initial value. So now we plug in 0 for x and -1 for y, and we can solve for that constant. Do it here. Don't wait, don't do it later. Do it here because it's solved for that constant. You see how that's nice? I don't want to spend the time to solve for y, which we are going to do, until I solve for that constant. That'd be silly. So if I solve for the constant now, all your variables are here. That is the constant. It's much easier than solving for y and then trying to find the c. You basically have to undo everything you just did. So plug in your initial value here. X is 0. Y is -1. 0 times all that stuff is 0. Sorry, I meant to C. So C is -2. Okay, let's plug that in. Let's solve for y. How in the world do we solve for y? Well, on the left-hand side, we could factor, couldn't we? So if we factor this, factor the y, and divide, we actually have an explicitly defined function that's a particular solution. And what it's saying is that we've now found the exact curve, the exact function that has this as its exact differential equation, or derivative in differential form, if you want. Man, I hope it's making sense to you. I hope that you're really seeing the finer points of the technique. Can you trudge through it? Yeah, but it's not as fun. It's much better if you understand it. My goal is to always provide that level of intimacy with it sounds awkward, with this problem, with this sort of technique. I hope I've done that. I hope you understand how these things relate. The very important point that you don't just assume it's exact until it meets the whole mixed partials being equal. Otherwise, you do not just start this without checking that, because you can go a long way and waste a lot of time. When they're not exact, I will teach you how to make them exact in the next video, where we talk about an integrating factor and how to use that. So I hope you enjoyed it. I hope that it's making sense to you. Hopefully you're encouraged that you're getting this, and I'll see you for the next video. Have a wonderful day.